In section 3.6, we're going to be defining inverse relations and functions. So let's do a quick review of the difference between a relation and a function. So a relation, if you're looking at a relation on a graph, you might see this. This would be a relation. It is not a function because it doesn't pass the vertical line test. If we want to see a function might be like this because it does pass the vertical line test. So a function is going to produce one output for every input, exactly one output for the input. An inverse relation is a result of exchanging the input and output values of a relation. Now that relation may or may not be a function. If the relation is a function, then it's going to be called an inverse function. So when we talk about graphs of inverse relations, let's suppose we have the two graphs that I have here in this picture. So you've got the blue graph and then you've got the red graph. Those two are inverse relations, and actually they're inverse functions. And the way you know that they are inverses is because if AB is on the graph of one, then BA is on the graph of the other. So let's take, for example, we have this point right here. That's the point 0, 1. If you look on the other graph, we should have the point 1, 0 on that graph. And so here it is right here. And that is a reflection across the line y equals x. So every point is a reflection across the line y equals x, and those two are inverses of each other. And so here's your line y equals x. Now, when we're working with these inverses, you're going to be asked to find the inverse from a set of points. You might be asked to find it from a graph, or you might be asked to find it from an equation. And in this video, I'm going to go through each of those and give you examples. So we're going to start out by finding the inverse from a set of points, and this is really easy. If you have this set of points, and let's say we don't know this is a function here, so let's say we have this set of points, and we want to find its inverse, and all we need to do is exchange the x and y values. So that becomes 4, -2, 1, -1, 0, 0, 1, 1, and 4, 2. And then we have the inverse of that relation. Okay, now let's say I would like you to find the inverse from this graph that we have here. Okay, so on this graph, you notice I have graphed this is the line y equals x. So you know that the inverse is going to be the reflection across the line y equals x. You can also take these points here. You can notice that it has several points, and find the coordinates of those points and plot those points, and then that's going to be your inverse. So, for example, this point here is the point -3, 1. So that means we want to graph the point 1, -3, and that would be here. Okay, and then we have, this is the point -1, 2. So we want to graph the point 2, -1, and that would be here. And then this we have the point -5, 2. So on the inverse is going to be the point 2, -5. And so then we can graph the inverse from those points. And that's not perfect. Here, I think I have a better graph down here. But you can see that it's the reflection across the line y equals x. Okay, now we're going to do it by giving the equation. So let's say I give you the equation y equals 2x plus 1, and I ask you to find the inverse of that. What you need to do, and the steps are here, you need to write the equation in terms of x and y, and that's already the case here. And then you want to exchange the x and y values. So this is going to become x equals 2y plus 1. All right, and then once you exchange those, you're going to solve for y. So I'm going to say x minus 1 is equal to 2y. Divide both sides by 2. And so y is equal to x minus 1 over 2. And that's going to be your inverse relation. Now this other example, a little more complicated. First of all, we have f of x, so we're going to write that as y is equal to 4x squared plus 2x. And now we're going to exchange our x and y values. So x is equal to 4y squared plus 2y. And now when you go to solve for y, you notice that it's a little more difficult because you have a y squared, you have a y. What you're going to use is the quadratic formula for this. So I'm going to set this equation equal to 0 by doing this and bring in over my x. And then what I'm going to do is say that is my a value, that is my b value, and that is my c value. And now that I have that, I'm going to use the quadratic formula. And this time I'm going to say y is equal to negative b plus or minus square root b squared minus 4 times a times c, which is negative x. And all of that is over 2 times your a, which is 4. Okay, and now we're going to simplify, so that gives me negative 2 plus or minus square root of 4 minus, or actually plus 16x over 8. And just continue to simplify. And we get negative 2 plus or minus square root. I can factor out a 4, so I'm going to do that. Okay, and now as I factor that 4 out, I notice the square root of 4 is 2, so I can then do this. All right, and then each, the 2, and the 8 each have a factor of 2, so I'm going to simplify that. And this is what we get. This is going to be our inverse relation. We're not sure yet whether or not that would be a function. Okay, so if we're going to determine whether or not an inverse is a function, then you need to know whether or not it's one-to-one. If it's one-to-one, then that means every input is going to correspond to one output, and every output corresponds to one input. And a good way to tell that is to look at a function and consider whether it passes the vertical and the horizontal line test. So for example, let's say I have a parabola. That parabola passes the vertical line test, but it doesn't pass the horizontal line test, because if you use a horizontal line, that horizontal line is going to hit at 2 points. Okay, so this function is not one-to-one because it doesn't pass a horizontal line test. It's only passing the vertical line test, which makes it a function, but not a one-to-one function. All right, now let's consider a line, a linear equation. That passes the vertical line test. It also passes the horizontal line test. So that means the inverse of this function, we'll call it f, is also going to be a function. So it is a one-to-one function. It passes the vertical and the horizontal line test. So now the other thing is, if it passes that test, then if this is the function f, then its inverse is going to be the f. So f inverse of x, okay? So this is the function f, f inverse, and this right here, this notation here, it does not, notice it does not mean this, okay? So that's the notation that we'll use for inverses. And now let's talk about composition of inverse functions. In section 3.5, we talked about composition of functions, and now we're going to talk about composition of inverse functions. If I have f inverse of f of x, and that's equal to x, and then I flip that around and say f of f inverse of x, and that equals x, then what we have, the situation that we have, is that those two are going to be inverses of each other. Okay, so in order to be inverses of each other, you must meet those two conditions. And here we have an example of that. So I have f of x and g of x. And right now, g of x is not called f inverse of x because I don't know whether or not they are inverses of each other yet. But I'm going to use this property up here to determine that. If I do, first of all, f of g of x, and what I want to get is x, I want to get x, and I also then come over here and do g of f of x, and I want to get x. If both of those conditions are true, then g and f are inverses of each other. So we're going to work through this problem. So let's start out with f of g of x. And that's going to be f of 3x over x plus 2. Okay, because that is my g of x there. Okay, now I go to f. F is my outside function here. And f is 2x over 3 minus x. Now, in those x spots goes this guy here. So that's 3x over x plus 2, 3x over x plus 2. Now, once I get that set up, it's just a matter of simplifying it. In this case, it happens to be a bit complicated. We're getting common denominators. So if I have 2 times the 3x over x plus 2, that's just going to give me 6x over x plus 2 over, and in the denominator I have 3 minus that 3x over x plus 2, which means I need to get a common denominator to combine those. So a common denominator for those would be the x plus 2. And so if the 3 needs the x plus 2 on bottom, then I have to multiply it by a fancy version of 1, which is x plus 2 over x plus 2, minus the 3x over x plus 2. It's already got the denominator we need, which is going to give me the 6x over x plus 2. That's the numerator. And in the denominator, I now have one denominator of x plus 2. And then I distribute my 3, and I get 3x plus 6 minus my 3x. Okay? And from here, you notice, hopefully, that those two, when you combine them, they cancel out. And now that I have a fraction divided by a fraction, I'm going to keep the first fraction, just dividing fractions, keep the first fraction the same, change the division, which this is your division, to multiplication, and multiply by the reciprocal. So the x plus 2 would go to the top, and then we are only left with 6 that goes to the bottom. So when I'm multiplying those two now, what you notice happens is these two cancel, the 6's cancel, and we're left with x, which is what we wanted. Now that you know that the first composition is equal to x, that means that we do actually need to try the second one. If the first one didn't equal x, either you made a mistake or it's not possible for the two to be inverses of each other. So the first one did produce x, which means I need to now try the second one, okay, which is g of f of x. So in this one, we've got g of f of x, and that's going to be g of, and I've got f of x is 2x over 3 minus x. And then I go to my g function, which is 3 times x over x plus 2. And now what I drop in those parentheses is what's in here. So it's 2x over 3 minus x, and then same thing here. And again, that came from here. All right, and now it's just a matter of simplifying. So in the numerator, I get 6x over 3 minus x over, and then in my denominator, again, I'm going to need to get a common denominator. So that means I need to multiply this guy by x plus 2. I'm sorry, not x plus 2 this time. 3 minus x over 3 minus x, because that's the denominator here, and the denominator of the 2 is 1. So when I do that, my common denominator in the denominator is going to be 3 minus x, and in the numerator I'm going to get that 2x plus 2 distributed to those two, which is going to give me 6 minus 2x. Okay, now I have this, and then what we should notice is that these two are going to cancel, and I end up with 6x over 3 minus x. I'm going to change the division again, which is here, to multiplication. Flip that second fraction, 3 minus x over 6. Again, you should notice that these are going to cancel, the 6's are going to cancel, and we end up with x again. Now, what that means is for g of f of x and f of g of x, we get x. So since we know that, then that means that these two functions are inverses of each other. And now instead of writing g of x as a g of x, it's actually now appropriate to say g of x is f inverse of x. Okay, Those two are equivalent expressions, all right? And that would be and by the same note, you could also write f of x as you could say that f of x is g inverse of x. Okay? And that's all I have for section 3.6.